Yeah, so first I'd like to excuse me, thank you for the invitation and thank Janosch for filling in when I was not ready. I don't have too much to say and I hope it doesn't take too long. The topics that I want to speak about are old topics, both closely related. The Chow group of zero cycles of a surface, and also some groups considered by Bloch, August, like cohomology at the generic point, but I'm really looking mainly at this. So yeah, one would like to describe exactly what this is. I'm always working over the complex numbers. It would be nice to say exactly what it is without conjectures, but even with all the conjectures in the world, it's still not absolutely clear. So that's the objective anyway. Okay. So since there are very few unconditional and unconditional theorems and of fairly general, the theorems of Mumford and Griffiths, so I'm going to start, well, I know everybody knows it, but I'm going to start with that and stay there for about 10 minutes at least. So let's recall. So the first theorem is from Mumford. Showed that if X is a surface, so smooth projective surface, with Pg not equal to 0, so H naught, yeah. Then the group of zero cycles is infinite dimension. So I want to say a little bit about this, and Roitman, who took up his work very soon afterwards, so this is around about 69 or 70, I'm not sure. And so it was generalized by Roitman, showed that even if X has higher dimension, if HIXOX is not equal to 0 for some I greater than 1, then the same conclusion holds. So I just like to talk a little bit about the method of proof. Roitman sort of streamlined Mumford's method. So often we are talking about cycles on X parameterized by something. The X's are always assumed to be smooth projective. The parameter spaces may or may not be. So if one uses a phrase like S to chow d of X, so everything is defined, as I said, over the complex numbers. So that is really, one is looking at chow d X base change to the generic point, and equivalently you are looking at the quotient group chow d of S cross X modulo all the cycles which, when you project onto S, they don't dominate S. So chow, well, it's not good to use upper notation, so okay. where S prime is contained in S not equal to S, and n is the dimension of S plus X, S cross X. Yeah. I'm not so sure that I'm writing the right thing here. Yeah. Well, not really. It's clearly wrong. It has to be corrected. Yeah. So. No, it seems okay. Yeah. It's not really okay. Okay. So, in any case, so associated to such a thing, there are of course cycle classes. Cycle classes. The simplest one is just an coherent sheaf cohomology with values in omega d. So you have cycle classes in HD S cross X. So omega d of S cross X. Excuse me. And this you can break up as a direct sum of sheaves. So, well, let me use whatever notation I've got here. So, P1 upper star omega. So that's a direct sum of those things, and then Kunet yeah, gives you lots of things there, but one omits a lot of them. And so if I've got this, if I write here a psi going from that, I have the class of psi. I'll call it the eth. So I'm looking at this particular sheaf and taking its cohomology, and it contains the factor H naught S omega E S, which means S over C tensor H D X yeah, so I said there are several factors and you can project that, and so the good thing is that you can put this inside the generic point. So yeah, so let's KS tensor ES. So writing it that way tells you that going modulo all this stuff here just doesn't matter. Okay. And then, so to continue with what Roitman is saying, is let's use the following relation. You say that is generated in dimension E if you have got a countable set with dimension Pn less than or equal to E, and such that when you take the images of these and take the subgroup generated by them, I should say for all n equals 1, 2, 3, etc., it's a countable set such that the subgroup generated by the images of the Pn beg your pardon? Yes, yeah, indeed. Yeah. Equals right. And what he says is that, so if maybe I should have said some things here, like when I put E equals 0, it's and assuming S is connected, this is just the cycle class of the any member of the family you're looking at. Then when I put E equals 1, you're measuring the tangent space. Mumford makes it a point talk about tangent spaces, and then he essentially takes E equals 2, generalization. So, so what Roitman actually proves is that if there exists, let me write it this way, S to Chowdy X such that class E of psi is not 0, then Chowdy X is not generated, and dimension less than E. Yeah. And in particular, if it's, so this next part is from Mumford, who says that if Chowdy X is finite dimensional, so this time we are not talking about subgroups generated by, but actually the whole lot of them, and it's parameterized by a countable number of varieties with dimension bounded above, then it's easy to see that is generated in dimension less than 1, because you can have a curve surjecting on abelian varieties, essentially what it amounts to, dimension 1. Right. And then of course there is a certain absence of cycles, since we don't know most conjectures like Hard-Lefschetz and so on, but you always have the diagonal in the product. So taking S equals X and D equals dimension X, and your xi to be the diagonal in S cross X. And when you write down these corresponding things, you get the Poincare duality theorem, meaning, sorry, what I meant to say is when you write down the class of the diagonal, you get it from Poincare duality with respect to Serre duality, etc. We get class E of xi is an H naught S omega E S tensor, whatever its dual is, by Serre duality. So is non-degenerate. So that was the style of proof. And so thus, yeah, so that gives the statement that I, Roitman's statement there. So thus, H naught X omega E X is not equal to 0, and E is greater, I should say if they exist E greater or equal to 2, etc., then Chow upper D, which is same thing, this is infinite dimension. So that was the statement. Roitman also proved. Yes. No. You mean here for this? No, for the D for which it holds. If you had a cycle going to Chow upper D, so all these things had a fixed D. Now D is the dimension, so I get 0 cycles. And then, yeah, okay. So that's the style of the thing, but then we have the diagonal, so from now on we are talking about 0 cycles. So Roitman has 2 more theorems. So this is his take on Mumford's theorem, pushed it a long way. He also showed that the torsion, so this is for now for 0 cycles, showed that if you look at, so chow 0 x, there is always a natural map to from that to the Albanese of x, and of course this could be huge, but thank you. Yeah. So yeah, degree 0 cycles. Yeah, degree 0 0 cycles. I'm not sure where to put the second 0. Yeah. Yeah, so you have this map, and independent of how large the domain is, he shows that this is an isomorphism on torsion. And then he also showed that if this is finite dimensional, so we are looking at, well, 0 cycles, so let's take 0 cycles of degree 0. So if there is a finite dimensional, well, a parameter space that covers everything here, then that's what finite dimensional means, then in fact this map is an isomorphism. And as I said, of course, all this still doesn't tell us when a particular 0 cycle is rationally equivalent to 0 or not. This only shows, so if I fix a P naught, so if let's take x is surface with PG not equal to 0, fix, say let me call it P naught in x, by which I mean xc. Then this x minus P naught as an element is not 0, or maybe let's write it in a contra positive way. The collection of x, so that x equals P naught in chow, is a countable union of closed subvarieties of x proper, of countable union. Let's write it as C1, C2, etc., and P1, P2, etc. So these are curves in x, and these are points in x. And then I've done this just to say that both these things are countable. Of course, one doesn't have those things explicitly written down, and therefore one doesn't really know, given an x, whether something is 0 or not. Okay, so one could improve the situation a little bit with just a little bit by asking, given C to chow 0x, so this one here, sorry, are you talking about this statement here? Yeah, so actually it should be stated better as the standard thing. Everything in algebraic geometry is countable. Yeah.
I just wanted to know whether
Yes, it is that. It is that statement. Yeah, yeah, that's right. Yeah. Countable union of varieties, and then you intersect with something, you still have a countable union. So, yeah, so where C is a curve and this is a surface with PG not equal to 0, so yeah, so you can ask, does there exist? It's still not saying so we're going to call it psi. So this will be written as C goes to psi C. Does there exist a C in C such that psi C right? Which is slightly better than this because X is two-dimensional and you are picking up a particular family. It's quite easy to do. To talk theoretically about this, of course, I need intermediate Jacobians. So let's recall Griffiths. So we have defined the intermediate Jacobian associated to a Hodge structure. Yes. But I'm going to stick to codimension 2 cycles, largely due to lack of courage as to what conjecture should be made when the codimension is bigger than 2. But so, because yeah. So first you've got the cycle map. So here dimension of X is arbitrary, and I'm writing it down only for codimension 2 because that's the only thing I'm using in this lecture, and a little more, yeah. So we have Chow2X to the Hodge classes, H4XZ, and then from the kernel of this, so those cycles which are homologically trivial, Griffiths define this map to the intermediate Jacobian, which in this case would be H3XC mod the second part of the Hodge filtration plus H3XC. Right. So let's call that the Abel-Jacobi invariant as he does. And as we all know that using this, he gave the first examples of homologically trivial cycles which are no non-zero multiple of which is algebraically equivalent to 0. Now unfortunately one doesn't know what the kernel of this is. So I'm going to just write down some conjectures here. So these should be treated as conjectures which are in keeping with the theory of motives, and at any rate conjectures for which it will be pretty hard to find a counterexample, and of course it will be good if somebody does actually. I think some skepticism is required. So A. So yeah. So I've got size in chapter X, and it's homologically trivial, and so it's and of course I should have said that this is the way it was done, but by now of course everyone knows that it can be done. It's an equivalent language of mixed Hodge structures. Yeah. I could say that size 0 in linear cohomology implies, so yeah, this is where I stress the 2, implies size algebraically equivalent to 0. And then B, so suppose in fact this is algebraically equivalent to 0, Yeah, I think it would be prudent to do that. Yeah. It would be prudent to do that because I don't know enough about torsion. And one states is torsion, is no torsion. That's right. That's Mercurius-Suzlin does it. Yeah. Theorems from K theory. Yeah. So, yeah. How about, by any case, okay, there exists and not 0 such that. It will be pretty good to prove that anyway. And of course, this I'd like to say is rationally equivalent to 0, but that can't possibly be true because Mumford contradicted that right at the start. So one had to put an assumption so all these things implies psi is rationally equivalent to 0 equals 0 in chalk to x. Yeah, so it's rational, right? So they stop being true if you formulate it exactly the same way. Yeah, but you could formulate it another way. So I'm coming to that. Yeah, I'm coming to that. So the first thing I want to say is that here, if dimension x equals 2, I never stated what Bloch's conjecture was. This is precisely Bloch's conjecture. So this is same as Bloch's conjecture, because 0 cycles are anyway algebraically equivalent to 0 if the degree is 0. So this is which would say that chow 0 x degree 0 to the Albanese of x is an isomorphism. The Albanese is taken care of by the intermediate Jacobian. Okay, so about this conjecture, the first thing, so I talked to Claire yesterday and she pointed out to me that so this is explained to me yesterday that conjecture A implies Bloch's conjecture by, so if x is your surface with PG equal to 0, then you always have the diagonal minus some other stuff. I don't know whether I want to write it out. Well, minus x cross p a point minus d times x cross, but this is not even exactly correct. So these are curves minus various c prime I cross c prime j and then minus etc. So one can always construct a cycle like that which is homologically trivial, and yeah, we can also manage 0 in the Albanese. You see an H1x tensor, H3x factor, etc. So I won't go into this in detail right now because it looks unnecessary. Yeah. And then one uses her argument about Kimura finiteness on curves, which you can do once you have got a cycle which is algebraically equivalent to 0. So this is algebraically equivalent to 0. And then which implies that as an operator it's nilpotent. So what is this operator? It goes like taking an x goes to x minus p, the diagonal, yeah, we're pulling up, pushing forward, etc., minus stuff supported on CIs, stuff supported on CI, on various CIs. Right? The di I should have said is a divisor in x cross x. Yeah. So the fact that this is nilpotent will tell you that everything is supported on this finite bunch of curves which shows it's finite dimensional, and use Roitman to say that if it's, then it's the Albanese. Right? Okay, so that is one remark. And yes, so this morning, so I was trying to find out from others where these conjectures are made so as to attribute them to the right sources. And then I found out from Deepam that conjecture A is actually a special case of, okay, so in Bailensohn's famous paper where he makes all these conjectures, he has a version of the Hodge conjecture which in fact needed to be modified, because of Mumford's theorem, infinite dimensionality, which wasn't taken into account, but it was modified by Janssen, Uwe Janssen, and actually that conjecture, so let's call it BHJ conjecture. BHJ. So first of all, I should make clear I'm talking about conjecture A is implied by BHJ. Yeah. So yeah. So if you apply this to the given cycle, will show that so I should say something. If something vanishes in the intermediate Jacobian, you actually get a Hodge class on the complement of that curve, and this says that that corresponding Hodge class has got to vanish on a smaller Zariski open set, which is another way of saying applied to yields that there is a divisor in X, so codimension 1 is effective divisor, such that support of psi is contained in D, and yeah, and the class of psi is yeah, so class of psi goes to 0. I'm always thinking of 3 folds, and so I was going to write H2, but you have to write the appropriate thing there, which is H twice dimension X minus 4 of D.
That's why you said it's like you managed to get a Hodge class of the complement of curve.
I said curve? Yeah, that's right. Yeah, I was thinking of 3 folds. So, okay, but then there is a theorem of Bloch and Ogus. We show that vanishing in just one dimension bigger, this is like codimension 2 thing vanishing on a codimension 1, is exactly the same thing as algebraically equivalent to 0, implies that psi is algebraically equivalent to 0. So this is a case where this is easy to show if you are tensored with Q, but they do it for any coefficients whatsoever. And now to answer Patrick's other question, what if you are not looking at codimension 2? Well, you could still apply Berenson-Hodge and get a statement which would be that it vanishes on, you can include the support in a divisor and it would vanish. That of course does not imply algebraically equivalent to 0, and it can't, shouldn't rather. So going much slower than I should. All you have is a codimension 2 cycle. Like let's work with 3 folds, which yeah. Okay, but that nevertheless is Bloch. It's a Bloch-August theorem. Yeah, which I think if I had to prove it without using them, I would use Deligne's mixed Hodge structures, and therefore there would be a tensor Q. Yeah, so that's so right. If we are not fussy about torsion, we could just straight off from Deligne. Okay. So now finally let me get to the point with this prelude. So yeah, there is no more to be said about those conjectures. At least I don't want to say anything more. Not right now. Yeah. So finally we can address the problem at hand. So your X contains a bunch of curves. So let me take okay. From now on, X is a surface. Smooth projective surface PG may or may not be equal to 0. And C is a curve, so C is C1 union C2. Maybe I can't use C's for everything, so these are all irreducible in X. So I can take their non-singular models and take the pick 0, take the Jacobians. So let me call A of D is the direct sum of the Jacobian of the non-singular models. And there is a natural map, of course, from this to Chow 0 of X. And I'd like to find out what the kernel is. There's also a map to that. So so I want to get, it's called okay, PD is the kernel of the composite. So it's the stuff that goes to 0 all along. And then you'd like to detect whether it goes to 0 in Chow 0 X or not. Because this is an abelian variety, and up to isogenies, you could write it as, P1 cross P2, and then one should be actually PM, where these are simple abelian varieties. And actually one should collect the various isomorphic factors together and look isotypical components. but let me just, so given one of these things here, you have got these maps to that which goes to alb x, and this composite is 0. So you could, it's not necessary, but you could take a curve C which maps to that, and so that the Jacobian surjects Pi is onto, right? And so this is giving you a thing from chow 0, chow upper 2 of x. So this gives that, and then you have some freedom here. If I want to represent this as a cycle of, because remember you can always take points of the curve cross divisors in x. You have some freedom there, and you can do some adjustments so as to make sure that it's first of all homologically trivial. So you represent this by that. You have some choices, homologically trivial, and then let's take a look at the intermediate Jacobian. Well, first of all, I should have said that the fact that it is, this composite is 0 says that this Hodge component is 0. The element here is 0, and so nevertheless you do get a well defined element in the intermediate Jacobian. You get aj psi in the intermediate Jacobian of the various parts, and the one we are interested in is h1 of c tensor h2 of x, but because you can add points cross stuff, you will have to do that. You will have to take the transcendental part of the cohomology. You get a well defined element there, and so yeah, so it's there. And so of course if aj psi is not equal to 0, and by which actually I mean is not torsion, sorry about that, then psi c is not 0, in fact not torsion, except for a countable subset. C belongs to a countable subset of the curve. So one would love to say that the converse is true, but it doesn't seem to follow from what I've written down. So, but it is true if you assume Bloch-Beilinson. I mean, since I'm running out of time, I will skip that. So, Bloch-Beilinson filtration plus the F2 is what we think it is, kernel of the intermediate Jacobian, kernel of AJ, implies that the converse is true. Now when you are talking about 0 cycles, this is yeah, so you have infinitely many abelian varieties there, uncountably many, one coming from each curve in X, and if you believe this conjecture, then you know almost what the kernel is. The kernel contains an abelian variety, abelian subvariety, and once you go modulo the abelian subvariety, you are getting a countable group. Okay, but we don't know what the countable group is, and you can ask, well, can you determine that? Yeah. So that would be the question, and you can decide whether what's coming next is an answer or not. Okay. So now I want to start with the Bloch-August situation. It's much less than that. Okay. So here's what seems very encouraging. So given x, this time, well, I'm going off surfaces just for a moment. I could define HQ of the function field to be the direct limit over all Zariski open non-empty of HQ using singular cohomology with Z coefficients. So that's a definition. And so now if you apply, okay, so here this is good notation because it doesn't really depend on x but only the generic point. But here if x is smooth projective, smooth and complete, because I'm going to use Poincare duality. So this is the direct limit over f contained in x not equal to and Zariski closed of h 2 dimension x minus q of x comma f. Yeah, and this certainly depends on x as written, meaning the other and all that. So let me just abbreviate this to h. I need something. Okay. What do we know about these groups? Let's take q equal to 1. So if you have a curve from the first cohomology of an open curve, or in fact, maybe it's better to state it the way the Abel-Jacobi theorem is stated. So taking dimension x equals 1, here it means you're looking at curves comma points and you're looking at first homology, and then we integrate global differentials and the kernel is principal divisors. So for q equals 1, whichever way one writes it, h1 bar x to the dual, which is h1 x ox, and the kernel is precisely kx cross. So this is exact. So you can ask what happens for higher q. So this looks sort of encouraging that these groups can be studied. Yeah. So now let's take x to be of dimension 2. Yeah, actually let's repeat that proof in higher dimension. Yeah, it doesn't matter whether, okay, is anything for the moment. Yeah. So so q equals 1 again, and in general this is Deligne's complex, his log d complex, because if you've got u contained in x is Zariski open, then after blowing up etc., the x will have got blown up and it's something else. Is that a divisor with normal crossings? And the first cohomology of u, this time with complex coefficients, is would map to H1 UXO, excuse me, and here it is H1 x omega x log d. When I write a 1, I mean a 0. Yeah, it's there. So if I start with an integral class, yeah, surjection is always easy by decreasing your u. You have a well-defined map there. And so we get our old favorite argument. You have an integral class. If it goes to 0, there is coming from a differential form with integral periods. So you take the indefinite integral and multiply by 2 pi I and exponentiate. So that tells us what's going on. So we can, with courage, use Deline's log complex again. So let's take q equals 2, and let me take dimension x equals 2, even though it's not required. So in this case, I see that I get a map from HQ of kx, H2 of kx, which is the same thing as what I called H2 bar of x, to H2XO direct sum the non-singular models, direct sum C contained in X, maybe D. These are irreducible curves, and here you will get H1 D tilde the structure sheet. So you have this map. You might ask, how large is this image? So this, by the way, is really graphic. So what you have is, that's your homology class, sigma in H2 xd. By Poincare duality, you have converted into something that you can integrate on, and then you can integrate a 2 form here. So these things are in D2, etc. So these boundaries are paths, meaning one chains supported on that, and then you can take an integral omega I di, where yeah, so these are in H naught di tilde k. Yeah. So there it was surjective, and you can ask, what is it here? Is it surjective? No, in fact, it's almost exactly the Chow group. So so before asking about the image, one should first ask about the kernel of that map. Which is, in fact, in Beilinson-Hodge conjecture. So Beilinson's conjecture. So let me say something. If you look at it from the point of view of cohomology, saying that the map to H2 XOX and the remaining stuff is all 0 is saying that you're looking at a second cohomology class of an open set which is integral and of type 2, 2. So says that the kernel of this map to H2XO, and this is not just for surfaces, and then he does a Q tensor that is precisely of the, it's in whatever comes from K2. df by f, I've got to put a 1 upon 2 pi I. Okay, I don't have to rub it out. Is in the span of Q span of these things. F and G are rational functions on X. So you can ask what's the co-kernel. So maybe I should have given the map, and this map is going to get changed. I'm going to omit this factor. So we have this map from H to Kx, let me call it theta, to direct sum H1 d theta O, where d contained in X is irreducible curves. Go through the whole lot of them. So in fact, easy calculation shows that you have 0 to z to chow 0 of x to co-kernel theta to h1 of x. So this I mean integer coefficients to 0. So even with conjectures, so whatever one said in terms of intermediate Jacobians and just threw off as a conjecture because one didn't know how to handle it, is actually saying the following from this point of view. There is no reason why the image of this should be a complex linear subspace. But when you take its image, so in other words, you take the image of theta intersected with a finite direct sum, you can ask for the largest complex subspace contained in that, and that's being dictated by those intermediate Jacobian conjectures. Yeah. Yeah, I have about 2 more things to say. I will finish in a moment. Now, of course, codimension 1 cycles, functions, everything is beautiful, and everything beyond that is a headache. And so I was misled, though it's not clear. Actually, it's not clear. So suppose C is a curve, then you've got 1 to Kc. Oh, well, I already wrote down that exact sequence. It's somewhere up there. Of course, yeah, it's right here. So if I have a surface and I want to understand second cohomology, the viewpoint is this, that these are motivic, meaning they are, it's a direct limit of homologies or varieties, and these are home into the 0 part of that. If I'm working with homology, so they are negative weights. So this complex vector space, which is all important, has been given a motivic structure. So one thinks that if you just work with a pencil and do so X is a surface, and I can try to apply that fiber by fiber, and will one get a motivic structure on say H2XOX, because after all it's the first cohomology of the direct image and everything else is motivic. It's unfortunately it sort of breaks down for the following reason. So I think I've run out of time to state precisely what I'm going to say, but you can, this will push forward the earlier thing, but then we don't want to let go of the usual topology, because then we are done for, we are back to nothingness. So this is what I call, you'll get something, and I can define this. And this is the direct limit. So this is a very explicitly defined, which I'll also just call H1 k x by p1, whether or not it makes sense. I can make this precise enough. I can, but I'm out of time. But here's the problem. You get that. If you just analyze carefully what you're doing, you get that. But you don't get a surjection. So we are working in the usual topology. And so if I take fiber by fiber, if I were to allow myself arbitrary analytic things and work in the Zariski topology in that sense, then this would have been perfect. It would have been a short exact sequence of sheaves. But I'm not quite allowed to do that if I'm working in algebraic geometry. I have to take these small pieces of things that extend globally. So our hands are tied. Everything here works, but where you end up is a certain subsheaf of this. And that ends some fantasy, but maybe it can be rescued. So that's all I have to say. Which one? This exact sequence here? Yeah. I mean, yeah, fiber wise, I mean, you're looking at an analytic or holomorphic algebraic vector bundles, and P1 is the same thing. It's going inside in the usual topology, in the holomorphic sections of that, but you don't have a surjection to holomorphic sections, because you're not allowing, whatever would require to make the proof work. If you work in a neighborhood of a fiber, you should be allowed to choose things fairly freely. Yes. They are defined by Deligne, right? Because you would always, you would have done a certain blowing up, and then you have the log complex. So, and the zeroth, so therefore this maps to OX, because that's the zeroth part. So HQ of that goes to HQ of that. Thank you.